On September 12, 2024, NASA's Perseverance rover drilled into a rock on Mars and pulled out something that changed everything. A core sample containing microscopic structures, tubular formations arranged in patterns with chemical signatures that 127 scientists across 19 countries now agree look biological. Here's the paradox. Despite being 140 million miles from the nearest laboratory, operating with 1990s computing power and a 22-minute round-trip communication delay, Perseverance has detected potential fossils with enough confidence that NASA is now planning a sample return mission costing $11 billion. The rock is called Chayava Falls, and what's inside it might rewrite the history of life in the universe. How is it possible to detect alien fossils on another planet using a robot the size of a car? And how much longer can Perseverance keep searching before its plutonium power source decays beyond usability? Perseverance launched on July 30, 2020, atop an Atlas V rocket from Cape Canaveral. But here's the counterintuitive detail. NASA almost didn't send it to Jezero Crater. The original mission plan targeted a different landing site, Syrtis Major, a volcanic region. But in 2018, orbital data from the Mars Reconnaissance Orbiter revealed something stunning about Jezero. It wasn't just an ancient crater. It was an ancient river delta. 3.5 billion years ago, a river flowed into Jezero, depositing sediment layer by layer. If Mars ever had life, a river delta was exactly where you'd expect to find it preserved, buried in sediment, protected from radiation, locked in stone. But Jezero was also the most dangerous landing site NASA had ever attempted. Steep cliffs, boulder fields, narrow safe zones, the special circumstance that enabled success. Terrain relative navigation. Perseverance carried an onboard computer that, during descent, compared real-time camera images to preloaded orbital maps and autonomously steered toward the safest patch of ground, dodging hazards in real time. It worked. On February 18, 2021, Perseverance touched down within 5 meters of its target. 5 key achievements established Perseverance as extraordinary. Achievement 1. MOXIE oxygen production. The Mars Oxygen In Situ Resource Utilization Experiment successfully converted Martian CO2 into breathable oxygen, proving we can generate rocket fuel and life support on Mars. It's run 16 times, producing 122 grams of oxygen. Not much, but proof of concept for future human missions. Achievement 2. Ingenuity helicopter flight. Perseverance carried a 1.8-key helicopter named Ingenuity. On April 19, 2021, it became the first aircraft to achieve powered, controlled flight on another planet. Ingenuity was designed for 5 test flights. It flew 72 times before a rotor blade damaged beyond repair ended its mission in January 2024. Achievement 3. First Mars sample cache. Perseverance has drilled and sealed 24 point for rock cores in ultra-clean titanium tubes, creating the first-ever sample cache on another planet. These tubes are stored on the rover and, in some cases, deposited on the Martian surface as backup, awaiting a future sample return mission. Achievement 4. Discovery of organic molecules. The Sherlock instrument detected organic compounds, carbon-based molecules, in multiple rock samples. Organics don't necessarily mean life, but they're a prerequisite. Achievement 5. Chayava Falls core sample. On July 21, 2024, Perseverance drilled into a reddish rock in the Neretva Vallis region of Jezero's ancient river channel. The core, nicknamed Chayava Falls, contained 3 simultaneous anomalies: tubular structures resembling microbial fossils, organic molecules, and leopard spots. Oxidized iron zones, suggesting chemical reactions life could exploit. It was the convergence of these three features, morphology, chemistry, and energy gradients, that made scientists take the possibility of fossils seriously. Two rovers, two craters, two completely different Mars stories. Curiosity's path. Curiosity landed in Jezero Crater on August 6, 2012. Its mission: determine if Mars was ever habitable. Gale is a 154 km wide impact crater with a 5.5 km high mountain, Mount Sharp, in the center. Curiosity has spent over 12 years slowly climbing that mountain, reading Mars's geological history layer by layer. What Curiosity achieved proved Mars had liquid water, neutral pH lakes, and organic molecules billions of years ago. Found complex organic compounds, detected methane fluctuations in the atmosphere, established that ancient Mars could have supported microbial life. But Curiosity wasn't designed to find life, just habitability. Its instruments can't definitively distinguish biological from geological organics. Perseverance's path. Perseverance landed in Jezero Crater on February 18, 2021. Its mission? Actively search for signs of ancient life and cache samples for return to Earth. Jezero is smaller, 49 km wide, but geologically younger and more diverse, with that river delta deposit. What Perseverance achieved? Found potential biosignatures in rock chemistry and morphology. Created a returnable sample library. Proved aerial mobility on Mars. Generated oxygen from the atmosphere. Perseverance was explicitly designed for astrobiology, with higher resolution cameras, more sensitive organic detection, and sample caching capability. Current status comparison. Curiosity, 12.5 years on Mars, traveled 31.5 kilometers, still climbing Mount Sharp. Wheels showing significant damage, RTG power output declining but stable. Perseverance, 3.75 years on Mars, traveled 27.5 kilometers, exploring the delta margin, all systems nominal. IRTG operating at 95% of launch capacity. Here's the relativity trick. Perseverance has traveled 27.5 km in less than 4 years. That may not seem like much, about the distance of a city marathon. But imagine walking a marathon where every step requires analysis. Is this rock safe? What's its composition? Should I sample it? And you can only take one step every few hours. And if you fall, there's no one to help you up. Ever. What Curiosity achieved? Established ancient Mars was habitable, wet, chemically diverse, energy-rich. What Perseverance achieved? Found candidate evidence that something actually lived there. The difference is staggering. Two commonly confused terms: biosignature versus contamination. Think of a biosignature as circumstantial evidence. It's a pattern, chemical, morphological, or isotopic, that's consistent with life but not absolutely proof. On Earth, we see tubular microfossils in ancient rocks, organic molecules with specific carbon isotope ratios, and fine-scale mineral layering from bacterial mats. Finding similar patterns on Mars suggests biology, but doesn't confirm it. Biosignatures can have non-biological explanations. Tubular structures might be mineral formations. Organics might arrive via meteorites. Isotope ratios might reflect geological processes. Think of contamination as the nightmare scenario. Perseverance was assembled in clean rooms, baked at high temperatures, sealed in sterile containers. But Earth is covered in microbial life. A single spore, a fragment of DNA, a molecule of organic residue hitchhiking to Mars could create a false positive, making Mars look inhabited when we're really just detecting ourselves. NASA's planetary protection protocols are extreme. HEPA-filtered clean rooms, UV sterilization, heat treatment at 110 degrees C for 50 hours. Perseverance's sample tubes were pre-sterilized to levels that would kill any known Earth organism. But any known organism leaves wiggle room. The exact moment of transition, when Cheyava Falls went from interesting rock to potential fossil, came when multiple independent analyses converged. Sherlock detected organic molecules at 10^100 parts per million, higher concentration than in surrounding rocks. PXL mapped iron, calcium, and phosphate concentrations in the leopard spots, chemical gradients consistent with biological redox reactions. Mastcam Z imaged tubular structures, 1 to 1, 2 millimeters long, some showing segmentation, morphology resembling fossilized microbe filaments on Earth. All three lines of evidence, in the same sample, at the same time. Timeline context, 2021, Perseverance lands, begins reconnaissance. 2022, first organic-rich samples collected in Delta region. 2023, rover enters Neretva Vallis, an ancient river channel with exposed bedrock. July 2024, Cheyava Falls core drilled. Initial analysis shows anomalies. September 2024, after 2 months of repeated scans with every instrument, the science team convenes. Consensus forms. This warrants sample return priority. 2025 present, Cheyava Falls becomes the most analyzed rock sample in Perseverance's cache. Every new scan adds detail, but also raises questions. The significance: if Cheyava Falls does contain fossils, it's the first time humanity has found evidence of life beyond Earth. Not radio signals, not atmospheric chemistry from 124 light-years away. Physical remains on a neighboring planet we can visit. But the if is enormous. Definitive proof requires bringing the sample home, slicing it into thin sections, examining it with electron microscopes and mass spectrometers no rover can carry. That's where the real challenge begins. Restate the core mystery. How does a car-sized robot on another planet detect potential fossils without a human geologist looking over its shoulder? The answer lies in an orchestra of instruments working together. Think of Perseverance as a robotic field geologist carrying a backpack full of labs. Each instrument is a specialist. Mastcam Z, the eyes. Twin cameras with zoom lenses, capturing color stereo images at resolutions down to 100 micrometers per pixel at arm's length. Sherlock, the organic detective. A UV laser that hits rock surfaces, causing organic molecules to fluoresce at specific wavelengths. It can detect organics at parts per million and map their distribution. PyXL, the elemental mapper, an X-ray fluorescence spectrometer that identifies every element present in a rock and maps them at pixel scales finer than a grain of sand. SuperCam, the zapper, a laser that vaporizes tiny spots on rocks from 7 meters away, analyzing the plasma glow to determine composition. It's fired over 1.3 million times on Mars. RIMFAX, ground-penetrating radar, sends radio waves into the Martian subsurface and listens for echoes, mapping buried rock layers up to 10 meters deep. Together, these instruments can image a rock, zap it to check composition from a distance, drive closer and scan for organics with UV, map elemental distributions with X-rays, drill a core sample and seal it in a sterile tube, and look underground to see what layers are buried. Signal travel time perspective ladder. Layer 1. Perseverance's computers send commands to instruments. Travel time, microseconds. Layer 2. Perseverance radios data to the Mars Reconnaissance Orbiter passing overhead. Travel time, roughly 10 seconds. Layer 3. The orbiter relays data to Earth via X-band radio. Travel time, 11:22 minutes depending on Mars-Earth distance, currently about 21 light minutes apart. Total delay, you send a command from Earth. Perseverance receives it 21 minutes later. It executes. The confirmation comes back 21 minutes after that. Minimum round trip, 42 minutes. Every decision, drive forward, drill here, analyze that rock, operates on this time lag. Signal degradation by physical law. Perseverance transmits at just 15-30 watts. By the time that signal crosses 140 million miles of space, it's attenuated to roughly 10 to 16 watts per square meter at Earth. To detect that whisper, you need massive receivers. How massive the receiver must be? NASA's Deep Space Network uses 34-meter and 70-meter dish antennas. The 70-meter dishes are among the largest steerable radio telescopes on Earth. They're sensitive enough to detect a signal equivalent to a cell phone transmitting from Pluto. Perseverance communicates with Earth directly during certain orbital windows, but most data routes through Mars orbiters, MRO, MAVEN, or ESA's Trace Gas Orbiter, which have larger antennas and better views of Earth. The global network, the DSN, has 3 complexes: Goldstone, California; Madrid, Spain; Canberra, Australia, spaced roughly 120 degrees apart around Earth's equator. As Earth rotates, at least one site always has line of sight to Mars. This 24/7 coverage ensures we never lose contact. If Perseverance encounters a problem, stuck wheel, power glitch, software fault, we'll know within 21 minutes and can respond. But here's the terrifying part. Every command must be perfect. You can't undo a mistake. If you tell Perseverance to drive off a cliff, by the time you see it happening, it's already over. That's why mission planning takes days. Every drive, every drill operation is simulated dozens of times on Earth in a sandbox with a full-scale rover replica before the real command is sent. Finding potential fossils on Mars isn't fast. It's methodical, cautious, and agonizingly slow. But it works. Here's why the normal solution doesn't work. You can't recharge Perseverance. Mars is 50% farther from the Sun than Earth. Solar panels would work, but they'd be large, fragile, and dust-covered within weeks. Previous rovers, Spirit and Opportunity, were solar-powered. Dust killed them. Perseverance and Curiosity use a different power source, a multi-mission radioisotope thermoelectric generator. Inside is 4.8 kilograms of plutonium-238 dioxide. Not weapons grade, this plutonium can't make a bomb. But it's intensely radioactive, decaying with a half-life of 87.7 years, releasing heat. Thermocouples, devices that convert heat directly into electricity, surround the plutonium core. As long as the plutonium stays hot, the thermocouples generate power. Starting capacity at launch in 2020, 110 watts of electrical power. Current capacity in early 2025, approximately 104 watts, still 95% of original output. Why declining? Plutonium-238 decays exponentially. Every year, the RTG loses about 0.8% of its power output. Additionally, thermocouples degrade slowly from radiation damage. Projected power curve: Perseverance will drop below 100 watts around 2028, below 90 watts by 2035. The rover needs roughly 75 or 80 watts minimum to operate all science instruments and keep electronics warm during Martian night, which drops to 100 degrees Celsius. Conservation measures: selective instrument use. Not all instruments run simultaneously. Mission planners prioritize which tools to use each sol. Hibernation during winter. In Martian winter, nights are longer and colder. Perseverance uses more power just staying warm. Non-critical operations are paused. Optimized driving. Moving burns power. The rover plans efficient routes and sometimes stays stationary for days, conducting remote sensing instead of driving. Emotional artifact with finality. On January 25, 2024, Perseverance's cameras captured the final image of Ingenuity, the helicopter that flew 72 times, lying damaged on a dune after a rotor blade struck the ground. The rover took one last portrait, then drove away, leaving Ingenuity behind forever. It was a reminder. Everything on Mars eventually stops. Current minimal operations. Perseverance operates near maximum capacity in 2025. All instruments functional. Full mobility. Active sample collection. But the engineering team is already planning for degraded modes in the 2030s when power constraints force choices. Projected declining trajectory. 2025-2030. Full operations. Finish exploring Jezero Delta, collect remaining samples, potentially climb crater rim. 2030-2035. Reduced operations, drive less, use fewer instruments per sol, prioritize high-value targets. 2035-2040. Minimal operations, stationary science, intermittent instrument use, focus on long-term atmospheric monitoring. 2040 plus, power below operational thresholds. Systems shut down one by one. Eventually, Perseverance goes silent, a monument on the delta it explored. Problem 1. Pebble stuck in bit carousel. December 2021, January 2022. After drilling the 6th sample core, a pebble-sized rock fragment fell into the bit carousel, the rotating mechanism that stores drill bits between uses. Why it's critical? The carousel must rotate freely to swap bits. A jammed carousel means no more drilling. No drilling means no more samples. The primary mission ends. The pebble was wedged against seals, meant to keep Martian dust out. Forcing the carousel could crack those seals, allowing contamination into the sample handling system. Automated solution attempt. Mission controllers commanded the carousel to gently oscillate, rotating back and forth in small increments. Over 5 sols, the vibrations gradually worked the pebble loose. Resolution. On January 15, 2022, the pebble finally dropped out. The carousel resumed normal function. Perseverance has drilled 18 additional cores since, without incident. Lesson: Martian rocks are brittle. Drilling produces fragments. The system needed gentler handling than Earth testing predicted. Problem 2. RIMFAX ground-penetrating radar intermittent failure. March-August 2023. RIMFAX began returning corrupted data packets. Some scans worked perfectly. Others showed static or dropouts. Why it's critical? RIMFAX is the only instrument that can see underground. It maps buried rock layers that guide where to drill. Without it, Perseverance is blind to subsurface geology. Diagnosis took 5 months. Engineers suspected a loose connector or radiation-damaged chip. They commanded RIMFAX through hundreds of diagnostic cycles, varying power levels, frequencies, scan durations, while analyzing the corrupted data for patterns. Discovery: the problem correlated with temperature. When RIMFAX's electronics dropped below 40 degrees during long, cold nights, a micro crack in a circuit board caused intermittent failures. Manual fix: new operational procedures restricted RIMFAX use to warmer periods, late morning through afternoon. Also, they reduced voltage slightly to minimize thermal stress. Resolution: as of 2025, RIMFAX functions reliably within temperature limits. The crack hasn't worsened, but it's a permanent weak point. Lesson: electronics tested to 55 degrees C on Earth still behave unpredictably at 100 degrees C Martian nights after years of thermal cycling. Future problem 3, wheel degradation, anticipated 2028-2032. Perseverance's wheels are aluminum, 52.5 cm in diameter, with titanium spokes and cleats. They're tougher than Curiosity's wheels, which developed holes from sharp rocks, but they're still taking damage. Current status: Minor dents and punctures visible in images, but no structural compromise. Proactive solution. Mission planners avoid the sharpest rock fields. Drive routes prioritize sandy or smooth terrain when possible. Engineers monitor wheel health with cameras after every long drive. Expected extension. If wheel damage remains gradual, Perseverance should remain mobile through the late 2030s, potentially traveling 50-plus kilometers before a catastrophic failure. The wild card, one bad rock, one steep slope, one wrong turn, could immobilize the rover instantly. Perseverance carries no spare wheels. If mobility ends, it becomes a stationary science platform. Still valuable, but unable to reach new sites or deliver samples to a future lander for return to Earth. Ongoing challenges compound as Perseverance ages. RTG power declining 0.8% per year, thermocouples degrading from radiation, wheels accumulating damage from sharp rocks, electronics experiencing cosmic ray bit flips and latch-ups, drill bits wearing down, only 6 bits on board, 4 already used extensively. Mission planners project full operational capacity through 2030. After that, declining power forces difficult choices. Estimated end of mobility, 2037 to 2040, when power drops below the threshold needed to drive and keep systems warm simultaneously. Time remaining from 2025 for full science operations, 5 to 8 years at most. That assumes no catastrophic wheel failure, no critical electronics failures beyond workarounds, no major dust storms that reduce solar heating. RTG powered, but dust affects thermal balance, and the sample return mission launches on schedule, currently targeting 2030 launch, 2031 Mars arrival. Every rock Perseverance drills, every sample it caches, every meter it drives toward the sample depot site. All of it happens within this shrinking operational window. The sample return mission is absurdly complex. A lander, a fetch rover, a Mars ascent vehicle, the first rocket launched from another planet, and a European orbiter to catch the sample canister in Mars orbit and ferry it to Earth. If any piece fails, or if Perseverance doesn't survive to deliver samples, Chayava Falls stays on Mars. The potential fossils, if that's what they are, remain 140 million miles out of reach. Forever. The clock is ticking. Not just for Perseverance. For our chance to hold a piece of Mars in our hands and know whether we're alone. Perseverance launched July 30th, 2020. Landed February 18th, 2021. Designed for a primary mission of 1 Mars year, 687 Earth days. It's now been on Mars for 1,370 sols, Martian days, nearly 4 Earth years. Almost double its planned mission duration. Compare its specs to modern tech. Computer, Rad 750 processor running at 200 ms, slower than a 1990s laptop, but radiation-hardened to survive Mars. Memory, 2 GB of flash storage, less than a single smartphone photo album. Camera resolution, 20 megapixels, decent, but not exceptional by 2025 standards. Power, 110 watts declining to 104, barely enough to run a bright light bulb. Yet with this ancient tech, Perseverance flew the first helicopter on another planet, generated oxygen from a CO2 atmosphere, detected organic molecules in ancient river sediments, and found candidate fossils. The paradox epitomized outdated technology, performing the most advanced astrobiology mission in history. Perseverance will continue exploring Jezero Crater through the rest of the 2020s, caching samples, climbing toward the crater rim, documenting Martian geology meter by meter. When power finally fails in the late 2030s or early 2040s, it will go silent. Wheels locked, instruments dark, sample tubes sealed in its belly and scattered on the surface. But those samples won't stay there. If the sample return mission succeeds, A fetch rover will collect the tubes, load them into a rocket, and launch them into Mars' orbit. A European spacecraft will catch them and bring them home. Sometime in the mid-2030s, if everything works, Chayava Falls will arrive on Earth. Scientists will crack it open, slice it thin, look closer than any rover ever could, and then we'll know whether the tubular structures are fossils or phantoms, whether the organics are biological or geological, whether Mars ever harbored life. Until then, Perseverance keeps rolling. Across ancient riverbeds, through delta deposits, over rocks that might hold the answer to the oldest question.